In Chapter 12, we'll start to look at global warming and the physical environmental changes that are happening as a result. First, we'll look at Antarctic warming, the West Antarctic ice shelves in particular, and then we'll look at Arctic warming, looking at Greenland, and also permafrost effect. Introduction to this chapter, the Earth balance of water in various states is quite delicate. For example, if temperatures warm, snow melts, and there you get more liquid and water vapor. You also get lower reflectivity as well. Ice is tied up in ice sheets, mountain glaciers, snowpack, and sea ice. Almost all the world's ice and snow is in decline, and the rate has skyrocketed since the 1950s. Polar regions are more sensitive to global warming, as an increase in heat has a more pronounced effect on cold regions than already warm ones. And this means that there was less energy in the system to begin with in the polar regions. If we spread a blanket of increasing energy from greenhouse gases across the world, that will represent a higher percentage increase of energy for the polar regions than for the tropical regions. But also very important for the polar regions is the ice albedo feedback on the land and ocean there. As these areas lose sea ice and or snowpack, that reduces the reflectivity, makes them able to absorb more solar energy, and will warm them even further. First, looking at Antarctic warming. Here in the center is the South Pole. It's considered east if you go towards the 90-degree east longitude from that area. It's also considered west if you go towards the 90 degrees west longitude from that area. Why I'm making a point of this is because really you're going north from all points from the South Pole, but this is how they do the mapping scheme. So East Antarctica is this enormous ice sheet that's high elevation, quite cold still, pictured here. And then West Antarctica, lower elevation in general, and this one's actively melting out. So this is the cover of your book. The credit for this picture goes to NASA. It's showing warming from 1959 to 2009. The units are in degrees Celsius per decade. And they are showing here that West Antarctica is warming at a much higher rate than East Antarctica. However, the entire continent is warming. Here we're looking at ice sheet thickness for Antarctica in meters. You can see areas where the ice is about 4 kilometers thick in East Antarctica. There's a couple regions like that in West Antarctica, but in general it's lower elevation. East Antarctica is an enormous ice sheet here. The projections for the East Antarctic ice sheet, the models suggest slight growth in the next 50 to 100 years. Why they project slight growth is because as we warm the globe, you're going to get more evaporation. That water vapor has a chance to go and converge over Antarctica, representing more precipitation. This area is too high and cold to melt significantly in the near future. These are places where the average temperature are well below freezing. And so a little bit of warming in the future still, they're going to have below freezing temperatures. The net effect for the East Antarctic ice sheet is more water vapor converging, turning to snow, and increasing the thickness of that ice sheet by depositing more snow on the surface. So the resulting decrease in sea level here, in other words, if you're piling up more snow on the East Antarctic ice sheet, you must be removing water from the oceans to do that. So the resulting decrease in sea level from those processes is very likely to be exceeded by melting in other regions. If we did manage to have this melt away in the distant future, the sea level equivalent of all that ice melting into the ocean would raise sea levels about 60 meters roughly for the East Antarctic ice sheet. The West Antarctic ice sheet has many ice shelves in the Ross and Weddell Seas here. Ice shelves are floating bases of the continental glaciers. The ice shelves are often anchored into offshore islands as well. These anchors, these ice shelves, can inhibit glacial flow on land. In other words, they're holding back the land glaciers somewhat and slowing down the progression of glacial ice calving into the ocean. If these ice anchors release from warming, for example, a warmer than usual current melts the base of these ice shelves, then glacial surge may occur. So this area is actively melting right now, and if it all melted, again, that wouldn't happen for quite some time, about 6 to 7 meters would be the adjustment in sea levels upwards. Question: glacial surge causes slippage of the entire glacier's base on top of the bedrock in a process called basal sliding. This generates heat due to friction. Would this be a positive or negative feedback for basal sliding? Would that increase the amount of sliding? And it would, of course, because it would melt and it would cause water, more lubrication, and that's a positive feedback. That's also very hard to model, to predict when that's going to happen. Here's just a figure summarizing these effects. The ice shelves are down here at the base. They're actually floating, so if you melt them out, it doesn't change sea level directly, because currently they're displacing the same amount of water that would represent into the ocean if they melted. But if you melt them, you lose these footings. and they're not holding back the land glaciers as much as they did, and you can get that glacial surge. And again, that's just a hard process to predict. And of course, when the land ice falls into the ocean, that does represent an increase in sea level, because now it's displacing water that wasn't displaced before, and the overall sea levels go up. One further process in there, a natural process, is that tides help to wiggle these loose as well. The IPCC AR5 report, looking at ice losses and gains over time, you can see that Greenland is clearly melting out, specifically along the continental edges, at a rate of about 10 centimeters of water per year. They're also showing extreme meltout rates in parts of West Antarctica, up to 14 or more centimeters of water equivalent per year, and this is over the time frame of 2003 to 2012. And again, we see some growth, a little bit of growth, in the East Antarctic ice sheet. This map shows you Greenland's ice thickness. It's really piled up in the center like a dome, up to 3 kilometers deep in the dome, and then considerably thinner as you go towards the coastlines. Warming very quickly, 9 degrees Celsius in the last 15 years in places. That is almost 18 degrees Fahrenheit, so that's significant. 7 to 9 meters of sea level equivalent if we manage to melt the entirety of Greenland's ice. Now this graph is looking at the seasonality here. We're looking at their summertime in the center in July and their wintertime on the edges of the graph. And you can see that we're looking at ice sheet albedo expressed in percent. So you're going to have fresh snow falling on the ice sheet in the winter, and that's going to brighten it up, make for a very reflective surface. And then during the summer, you're going to have natural melting processes, and that's going to reduce the reflectivity as you get more water on the surface that has a pretty low albedo compared to nice fresh snow. But over time, it has become less reflective in general every summer over the last 12 years that are shown in this graph here from 2000 to 2012. So the reflectivity is decreasing. With increased melting comes decreased albedo. That's a natural process. You get more algae contributions as well as you have more water. This effect is made worse each year by the continuous deposition of soot from increased northern hemisphere wildfires, but also industrial sources. So these are positive feedbacks. So this is kind of what it looks like in Greenland after significant meltdown. The process typically is that as the water melts out through the ice, you tend to get residual dust and it kind of aggregates at the top. So there's plenty of scientific research looking at this, and darksnowproject.org is one place you could get a variety of information from. Algal blooms also play a part in this. Large blooms of photosynthetic algae occur every summer, and they can decrease the reflectivity by 13% as a result. So they're tied in here too. Over time, if you add more water each summer, you're going to get more algal blooms. That might represent a positive feedback as well. This is a little bit more in its infancy, the research here, but here's a link to the Black and Bloom project, which looks at this. In a 2007 IPCC report where they had a general circulation model coupled to the Greenland ice sheet, they did an experiment where they did 4 times present CO2 amounts, getting up to about 1,500 parts per million CO2 in the future. They found sea level increase 1,700 years from the beginning of their model run would be about 4 to 5 meters, so significant, but a significant amount of time before that happened too. And the model runs starting at year 0 with a volume of 100%. You can see that most of the melt-off primarily happens along the coast first because it's lower elevation, warmer, and then eventually it starts to eat away at the dome after 2,000 years. So I'm just showing this to show that, yes, eventually the models are showing if we continue on a path towards increasing CO2, we will melt the entirety of the Greenland ice sheet. There is, however, quite a bit of time involved there, but it's still probably something we want to avoid. Now, those type of projections, as complicated as they are with a general circulation model tied to the Greenland ice sheet, they don't include other nonlinear ice dynamics. For example, a rapid collapse of the Greenland ice sheet if water lubricates the base of the ice sheet. This picture is showing what's called a moulin in Greenland, essentially a river of water that came from melting the ice that runs down into a crevasse somewhere into the depths of the Greenland ice sheet. So where exactly does this water go? Does it go to the middle of the glacier? Does it go to some lake in the middle of the glacier? Does it flow out to the edges of the continent? So NASA put in a number of ducts a number of years ago, with of course a return address on the ducts. And so since then, my understanding, only one of the ducks was found by a fisherman well off the coast of Greenland, which showed basically that that water did flow out eventually somewhere along the coast, but not much else. So parts of the ice sheet may be getting more lubricated at the base, which make them more likely to slide into the ocean. Although geographically, underneath this ice sheet, it appears that there's a ring of coastal mountains that would prevent a major slippage of the Greenland ice sheet into the ocean. However, this process may be important, and it's just one of those things that's really hard to model and figure out. So looking at the different processes in Antarctica versus Greenland, first off, Antarctica tends to have these ice shelves, and they tend to be melting from the bottom now, meaning that the ocean water is getting anomalously warm, and that's been shown in a number of papers, including this link to a Nature paper in 2012. So they're melting out. As they melt out, that might cause glacial surge of the land glaciers. Greenland, on the other hand, is melting from the top down. Greenland's ice is primarily melting from warm air above the glacier, so Greenland's melting from the top down. A lot of Antarctica is melting from the bottom up by this warm ocean currents eating away at these glacial footholds. Next, we'll look at permafrost. This is rock or soil material that has remained below freezing for 2 or more years. Some of it might have almost no water in it, and some might contain as much as 30% water. 18% of the Northern Hemisphere has permafrost underground right now. So this graph is looking at the distribution of permafrost. Continuous permafrost well to the north, just the whole land surface is covered with permafrost. Discontinuous permafrost, so there's spaces that are permafrost and spaces that are not. And then sporadic permafrost, which includes the Rocky Mountains here. There's patches of permafrost up in the tundra area and the high alpine. Permafrost is melting at a good clip in the Arctic and elsewhere. China, for example, 1 mile north retreat every year, so melting at a good rate. Permafrost temperatures and therefore meltout rates really respond to decadal temperature trends, as it takes a long period of time to really get into the soil and adjust the temperature in the deep soil. There's a slow conductivity of that temperature anomaly as it goes downward. So if you take a borehole, you drill a hole in the permafrost, that can give you the temperature profile. The IPCC AR4 showed some permafrost warming from 1950 to 2000. They owed this to higher air temperatures over time, but also changes in snowpack. Places that get a bigger snowpack are going to have more insulation, so the land surface is not going to see the changes in the atmospheric temperature because it's insulated. Here, looking at this graph, we're looking at boreholes from the same permafrost region in Mongolia. One from 1987 with the closed red squares, and one from 2004 with the open red squares. And you can see that the entire temperature profile has shifted towards more warm in that time frame. If permafrost has a high water content and it melts, a lot of things can happen. First of all, you can get drunken trees in the forest, so in places that there's permafrost all the time, biology has adapted to using the permafrost. In the case of trees, it uses it for stability to kind of anchor in there. If you melt out the anchors, the trees fall over, so to speak. And beyond the biology, people that live in permafrost regions depend on the permafrost stability as well. They have no choice but to build roads on top of it, housing on top of it, and when it melts, they have problems with that meltout because the stability changes. The other thing you can get is what are called thermokarst ponds, which essentially are big stagnant pools of water as a result of melting that permafrost and adding water to the land surface. Thermokarst ponds, again, if you melt that permafrost with a high water content, you tend to get stagnant ponds. This represents an anaerobic environment where you get methanogens that are simply organisms that create methane. But also, if you take away that protective ice layer by melting the permafrost, any methane that was trapped underneath there is free to bubble up to the surface now. And so both these processes are important. Methane's a greenhouse gas and quite a strong one, so this can increase surface warming locally but also globally. The prediction from the latest IPCC report, the AR5, it is virtually certain, their highest level statistic probability, it's virtually certain that near-surface permafrost extent at high northern latitudes will be reduced as global mean surface temperatures increase. By the end of the 21st century, the area of permafrost near the surface, the upper 3.5 meters, is projected to decrease by between 37% in the optimistic RCP 2.6 scenario to 81% in the business as usual scenario for the model average. So very significant changes there, very significant changes expected in the future. Key points for Chapter 12, Part 1. West Antarctica and Greenland are big players for future sea level rise and are currently melting. Feedbacks exist with black carbon and algae growth, specifically on the Greenland ice sheet. Nonlinear processes such as basal sliding and surge make the predictions a bit more difficult. Permafrost is melting out in the subarctic areas. This is leading to increased methane, representing a positive feedback that could be significantly important in the future.